Hello everyone, I'm Engineer Jonathan C. Pacaldo, a Doctor of Engineering student of the University of San Carlos, Cebu City, Philippines. I'm also a faculty of the Palawan State University College of Engineering, Architecture, and Technology. I'm happy to be part of the second Kuala Lumpur International Conference on Social Sciences, Education, and Engineering 2021. I'm here to share my study on hybrid renewable energy systems entitled Performance Analysis of a Hybrid Diesel Renewable Energy System in Cuyo Island, Palawan, Philippines. My co-authors are Dr. Michael Abundo of the Nanyang Technological University, Singapore, Dr. Las Dominda M. Villatinos of the University of San Carlos, and Engineer Carlito S. Baco Jr. of the University of San Carlos. Okay, so challenges facing isolated island communities is the lack of more efficient and sustainable solution to improve energy access and energy security in the area, which affects the community's long-term development. For these isolated island communities, the solution is diesel generation. But although it provides an on-demand power, the application has its drawback in terms of operations and logistics. Now, renewable energy utilization can be a solution, but unfortunately, it cannot cover the demands at all times. In such case, a hybrid diesel RE electrical energy system is highly recommended. With the use of Homeper software, a different combination of hybrid diesel RE electrical systems performance in terms of the lowest cost of energy, the renewable energy fraction, and carbon emission reduction will be analyzed in the island of Cuyo. Now, optimization results can be used for an adequate planning and integrating RE into an existing or new projects involving island off-grid distribution. Now, this study aims to deliver the optimal hybrid diesel RE electrical system for off-grid island community based on the actual load profile of the island and the available RE resources. What is hybrid energy system? A hybrid energy system generally consists of two or more than two renewable energy sources and energy storage components used together to provide increased system efficiency as well as greater balance in electrical energy supply. This system uses a wide variety of enabling technologies to overcome the difficulties associated with RE resource variability and allow RE generation to be smoothly integrated into diesel power systems, respectively. Now, what is Homer Pro software? Homer Pro was developed by the National Renewable Energy Laboratories, or NREL, and it stands for Hybrid Optimization Model for Electrical Renewable. Now, it can be used to simulate a grid-connected and off-grid system from village power to island utilities. Various combinations of energy sources, medium of energy delivery, storage, fuel options, and different types of loads are available for a variety of applications. It also has its sensitivity analysis algorithm, which evaluates different possibilities for any given system configuration. And it allows the user to compare different design options based on the economic and technical merits. Some studies done in the Philippines using Homer Pro. In Lamens and Tamayo, Homer Pro was used to estimate the energy consumption profile of rural health units in Los Baños, Laguna, and the result was used to determine the optimal hybrid solar energy systems design and benefits. Likewise, in Sumira, Parado, Castronocon, a framework for analyzing the techno-economic potential of hybridizing a sea vessel with solar photovoltaics, lithium-ion batteries, and diesel generators using Homer Pro was presented. Now, our methodology. First is the data gathering. Our data needs the load profile of the Cuyo Island. We also have our 9-year wind speed data from Pagasa Cuyo Station. We also have a 40-year wave incast data from Met Ocean View. And we also have our input parameters, existing diesel generators parameters. We also have our solar PV inputs, wind turbine inputs, wave energy converter inputs, battery and converter inputs. Then it will be optimized using Homer Pro. And lastly, we have our results, the lowest cost of energy, the renewable energy fraction, emission reduction, and RE technologies performance. Our study site is in Cuyo Island, Palawan, as you can see in the map. Cuyo Island is situated 278.37 kilometers northeast of Puerto Princesa City and has a population of 34,556. Now, average load demand of Cuyo Island is 0.984 megawatts with a peak demand of 1.4 megawatts. The average cost of energy is $0.235 per kilowatt hour. Now today, they have 6 DC generators in use with a load capacity of 500 kilowatts and 672 kilowatts. Now our renewable energy resources, we have our wind energy resource. Our wind energy resource is classified by NREL to have good to excellent resource potential for a wind speed of 30 meters. So as you can see the table in Pagasa, 30-year average wind speed data, Cuyo Island, so annual average wind speed of 5 meters per second at 4 meters elevation is a good wind data or a good wind resource. Our solar energy resource coming from the NASA prediction of borewell energy resource database, monthly averages for global horizontal radiation for over 22-year period from July 1983 to June 2005. The scaled solar resource of Cuyo Island is 5.72 kilowatt per square meter. Now, for our wave energy resource, our data is from Metocean View, 40-year INCAS data. So as you can see in the map, we have data points 4, 5, 7, 8, 9, 10, 12, 13, and 14. So the highest wave power density is 5 kilowatt per meter, data point number 5. Next are data points 13 and 14, which has 4.88 wave power density. In this case, we are going to use data point number 5 as our reference to for our wave energy resource. Now, our wave energy resource will be substituted by a hydro resource because Overpro does not have an option for wave energy resource, so the hydro power resource will be used instead. Now, using this relation, the power of the hydro is equals to power of the wave, in which we can derive the flow rate needed for hydro resource inputs in Overpro, which is equals to Q is equals to 0.05 times Hs squared times Te, where Hs is the wave height and T is the wave power. Now, substituting the wave height and period for data point number 5, our scaled annual average stream flow for Cuyo is 700.73 liters per second. This is our hybrid system architecture. So the hybrid system architecture consists of 6 generators, the existing 6 generators, the hydropower in lieu of wave. We have the wind turbine, we have the solar PV, we have the converter, we have the battery. Now the cost of equipment, we are going to, as you can see in the table, we have the latest US NLATV 2020 for inputs of the capital expenditures and the operating expenditures. We are going to use the latest US NLATV 2020, and for battery and converter, we are going to use the 2019 and 2020 studies. Now, for wave energy capital expenditures and operating expenditures, we have data from NREL 2012, the cost and performance data for power generation technologies, and we also have Ocean Energy Systems 2015, the international levelized costs of energy for ocean technologies. Now, the input parameters for diesel generators. We have here the replacement cost, the operation and maintenance cost, the fuel price, and the lifetime of our project is 25 years. And the solar PV inputs, we have our capital cost, we have operation and maintenance cost, and our surge space is from 0 to 300 kilowatts. We have wind turbine parameters. We are going to use Lithium 77850 kilowatts. And we have here the capital cost, the replacement cost, and surge space is from 0 to 6 wind turbines. Hub height is 65 meters. Now we have operating strategies. This part of the Power Pro simulation, the load following and cycle charging. These are the two operating strategies employed in hybrid renewable energy system. LFE strategy means that the RE system charges the battery storage system for the excess electricity produced while the diesel generators are only allowed to run enough power to meet the load demand in the absence of RE system. In CC strategy, diesel generators charges the battery storage system while simultaneously meeting the load. For this study, the simulation uses both LF and CC strategy to gain a more comprehensive result of a diesel RE hybrid electrical system. Here, the operating reserve are set to default values, the 10% load in current time stat, 80% and 10% as percentage of renewable output of solar and wind power output respectively. The base case. The base case are the existing case scenarios for Cuyo Island. The fuel cost is $0.68. The average energy cost is $0.34. Operation and maintenance cost is $14.4, and average energy use per day is $22.97 per kilowatt hour. The load factor is 0.41. Now, for our results and discussions. Now, after simulation, the lowest cost of energy, as you can see in the table, are the combinations of diesel wind, diesel PV wind battery converter, and diesel wind battery converter. As you can see, we have the Cuyo Island's average cost of energy is $0.235 per kilowatt hour. So our lowest cost is only $0.113 per kilowatt hour with 72.8% RE fraction. Now, as you can see in the lower part of the table, we have the diesel wind wave, diesel wind wave battery converter, and so on. They have the largest cost of energy because of the larger capital expenditures and operating expenditures at the present. Now, as you can see here, this is our diesel wind hybrid electrical system. Our Lithium 77850 wind turbine has 85.6% here, 85.6% production, no? The highest on the system. And the capacity factor is 60.6. So you can see the monthly electric production. Generators are only used to supply load whenever the wind turbine is not sufficient. Now, let's see the second highest, the diesel PV wind battery converter hybrid electrical system. Okay, so here the wind turbine only has a production of 73.1%, and the generic plate PV has 19.7% production. Okay, so now as you can see in the monthly electric production, almost for all the months except for May, June, July, August, and September, and a little bit in October, that our generators are being used. Now, the summary for the first and second lowest cost of energy. It is important to know that With regards to fuel savings, the diesel wind hybrid saves 72% of fuel, or about 1,567,646 liters of diesel, while for diesel PV wind battery converters saves 90.7% of fuel, or about 1,981,702 liters of diesel, because it has 89.4% renewable fraction. This is the combination of the solar PV and the wind turbine. Now, let's look at our wave hybrid system, or the hybrid system that includes wave energy converters. Here, we reduce the cost of our wave energy converters by 50%. And the result gives us that our diesel wind wave has only 0.201 per kilowatt hour. This is less than the annual average cost of energy for Cuyo of $0.235 per kilowatt hour. So meaning if the current capex and opex for wave energy converter can be reduced by 50%, its LCOE will result to a more competitive value and will be a good candidate in addition to wind and solar hybrid system. For our conclusion, for a diesel RE hybrid system to an island, and the best options are diesel wind hybrid system, the diesel PV wind battery converter hybrid system, and diesel wind battery converter hybrid system. It has the lowest cost of energy of about $0.113 per kilowatt hour, $0.114 per kilowatt hour, and $0.114 per kilowatt hour respectively. Now, diesel wind hybrid system, having the lowest cost of energy, has an excess electricity of about 88.6% and emission reduction of 71.8%. This means that this system can support additional future load as much as 88.6% of the existing load demand and has a significant impact on mitigating carbon footprint. Now, for hybrid combinations, which includes multiple wave energy converters, the diesel PV wind wave battery converter system has $0.373 per kilowatt hour cost of energy, but it has an RE fraction of 97.6%. This value means 97.45% reduction in carbon emission. Now, the levelized cost for wind and PV are $0.0291 and $0.0531 per kilowatt hour respectively. This is within the range of predicted values for 2021. While for the wave energy converter, levelized cost is $0.66 per kilowatt hour. Now, this is within the range of 0.20 to 0.90 kilowatt hour levelized cost for wave energy. But a reduction of 50% in capex and opex will make the multiple wave energy converters competitive in the market. Thank you. That will end my presentation. And for any comments and suggestions, you can write it in the comment section. Thank you and God bless everyone.